Thanks, Alan. Um, I'm going to try to distill some general highlights from a couple of decades of work on restoring or reconstructing new San Francisco Bay beaches. This started not with living shorelines initially. It started really with Goals Project and my former work at Fish and Wildlife Service with ecosystem recovery plans for endangered species. But I think in the current era, really that's been integrated into living shoreline work, which is expanding it beyond its original exclusive habitat focus and boundaries. And I think probably for the better, because it extends the range to a lot of land uses that otherwise would be difficult to integrate with pure restoration. So this is sort of a new era. And in doing that, I'd like to acknowledge two of my collaborators who I've been working with for those past couple of decades, Roger Leventhal and Dan Gillenwater, who worked on some of the pioneer projects before we had a lot of regional support for Bay Beaches and some of the earliest pilot projects. So next slide. Oh, by the way, that photo was Roberts Landing, now called Long Beach. It's one of the largest bay beaches left in the bay. Not an historic beach, but pretty close to where one was. And it's also up for a restoration plan. So starting with the text slide, I'll be reiterating this throughout the talk, but just to prime you, I'd like to go through a few of the key points that represent six selected general key features of living shorelines involving bay beaches. First, key point that Ellen mentioned is that beach projects are not quite identical with beach ecological restoration. One of the distinctive features is that they take as their lead goals the reduction of wave energy or the increase in shoreline resilience to erosion. And that is not necessarily something that beach restoration does. Beach restoration projects, pure and simple, can allow for a lot of shoreline retreat and instability. It's incumbent on living shoreline projects to serve both habitat needs, but also increase buffering of wave energy or increase the resilience of shorelines to recover from erosion events. So it's a sort of a dual purpose that can be integrated. From my experience, the most important one is for living shorelines involving beaches is to provide that alternative to traditional coastal engineered armoring. That is, all the design manuals, all of the professional experience leads to, at the first reach of erosion, emergency conditions, reach for armoring. And it's incumbent on living shoreline projects to show that they can provide equal or better performance for erosion reduction as traditional armoring with more benefits. And that's going to be an implicit focus of a lot of these slides. Another key feature of living shorelines is even where you're not restoring natural conditions in natural locations or natural systems, you can still use natural analogs, artificial versions or modified versions of called nature-based structures that use natural materials reconfigured for new purposes. So they're consistent with or congruent with natural features, but they're not really restoring historical natural features. And I think that actually opens up a lot of design opportunities and local site adaptations. So you don't just default to armoring or traditional engineering structures like brines. Another key feature of living shorelines involving bay beaches is sea level rise adaptation. Again, in vast open sanctuaries, preserves, you can allow beaches to appear, disappear, migrate. In living shoreline context, there's a greater need for predictability and nature-based, environmentally compatible erosion management, but you still have to provide some degree of erosion management that is an improvement on existing conditions, particularly where land uses adjacent to the shoreline demand it. And one of the key design features I'll probably be reiterating is the need, as Ellen mentioned, to adapt to local shoreline settings. This is the source really of all meaningful, feasible goals. Goals don't come from regional plans. They really come from the local setting. You can reverse engineer goals to fit a site and get a lot farther in meeting them than you could by starting with more abstract or generalized goals and then trying to shoehorn them into a site that resists them. That's a really important design principle, I think, and it serves both interests well. You can serve regional goals better by finding a good adaptive fit to local conditions rather than try to, serve all possible goals that might be imposed on a site. And finally, implicit in the first couple of goals is the need to design beaches to manage wave energy and erosion. There are different approaches to doing that. You can either dissipate more energy by providing more space for waves to break and lose energy. You can increase the resilience of the materials so that if there is erosion, they can come back and reconstruct themselves without engineering. You'll see some examples of that as you go further on. Next slide. I can't tell if it's there, it's advanced. This is my favorite pair of slides to illustrate the idea of coarser bay beaches as alternatives to riprap. These are literally paired slides. You're looking in the first the left side slide is looking south on the Salt Pond Bayfront levee out by Coyote Hills. I think that's Pond 2A. I'm not sure anymore. This is from 2014. It's over a decade old, so things have probably changed there. But as you look south, you can see a self-constructed, non-engineered gravel barrier beach that's connected to, it looks like a little islet. It's sort of a tombolo, which is a barrier beach connected to a little emergent island. It's a remnant of a 19th century historic landing that was built from local quarry materials in Coyote Hills. It's completely eroded, but the eroded remnants have shaped themselves into a little barrier beach. And one thing you can't see on that barrier beach among all the driftwood are lots and lots of western sandpipers. These are also high tide roosts. But if you look along the edge of the outboard side of the levee, you'll see that instead of riprap, which is what is the traditional erosion treatment for all of these outboard salt pond levees, there's no history in 50, 60 years, there's been no history of placement of rock or concrete slabs where this little barrier beach existed. And instead, salt marsh is creeping up the side of the salt pond levee and forming transition zones. So here is a natural system that is a great model for how you can use coarse, gravelly, particularly barrier beaches, to avoid the need for what's in the right-hand side, which is the same time period. That is legacy concrete slab riprap. That means it was placed before BCDC was regulating in the 60s. So there's a lot of accumulated material there, and there's no marsh. And you can see that waves are nibbling away at the top of that levee, providing inferior wave erosion protection. So this, to me, is like, there's one slide you remember from this presentation. Keep this one in mind. This is where you can use beach-based living shoreline treatments, again, combined with other habitats like marshes, to increase functions across the board: habitat, aesthetics, maintenance cost, and also engineering stability. Next slide. And these are, again, the same wave energy levels, same near shore slopes. There's no difference. You're looking north and south. So in the earliest generations of estuarine beach construction, from using those natural reference sites as models, like the ones on the right, the Brisbane Bayshore Gravel Spit, which was one of the reference sites for Arambaroo Island. These are not totally natural beaches. These are semi-natural. They're natural processes working on erosion of artificial substrates, like the Bayshore Fill along Highway 101 south of San Francisco. It formed a couple of recurved gravel spits. We studied those and used them as our own homemade design guidelines for treating Arambaroo Island, and also at Pier 94 in San Francisco at the Port of San Francisco. And following that same process as design, we fed the profile the appropriate grain size distribution, not too hard to measure, and waves reworked the play sediment into gravel barrier beaches or fringing beaches, which then rapidly reduced the rate of erosion along a previously rapidly eroding shoreline. I could go into the dynamics of how this works, but gravel basically infiltrates wave uprush or swash very rapidly. So there's very little energy coming down. So gravel beaches can get rid of a lot of excessive wave energy in a very short profile, which is why we're a little biased in using the coarser sands and gravels in these tight spaces where we don't necessarily have room for a full sand beach profile, even where they existed, where you can find coarser beaches sometimes do a disproportionate amount of wave energy reduction and erosion protection. Next slide. There we go. But it does not mean that beach restoration or living shorelines do a disservice for habitat benefits. Beaches probably are one of the better, estuarine beaches are probably one of the better examples of the belief that sometimes isn't always met with success about build and they will come. But wildlife, particularly shorebirds and terns, are very attracted to these highly whitish, reflective, or high albedo linear habitats next to water on one or both sides. They key into that behaviorally and they'll follow them wherever they pop up, even in the edge of the delta in Montezuma, where sand was placed for dredge sediment disposal. Least terns and snowy plovers follow the sand out all the way to the edge of the delta. One of the incidental benefits of living shorelines with an engineering priority is that they will still function as habitat if you can balance the recreational land uses and disturbance levels. You can sort of split the difference and have beaches serving both habitat functions and engineering services. And that includes below the beach profile, not on the beach proper, but as Ellen mentioned, low tide terraces below the beach, which are part of the shore face profile that is inherent in estuarine beaches in some locations in the Central Bay, and also even in the Carquinez Straits. These sandy mud terraces with generally lower turbidity than pure mudflats, these also create stable beds for eelgrass beds. Above is in West Berkeley. These are spontaneously colonized eelgrass meadows of low density. The upper one, West Berkeley, I've been seeing regularly occur there since 1991, at least during the epic drought of that era. They came in and they stayed. And even in the muddier zones in Whittle Marsh, the east side of Point Pinole, robust eelgrass beds. That's Professor Catherine Boyer. Hope she authorizes the, the photograph, but yes, significant compatibility with other living shoreline habitats. Next slide. I'm getting a little lag in the next slide, so this might be where I'm not speaking. And of course, one of the most important connections that proves that we have a somewhat false dichotomy between wetlands and beaches, particularly when you think about the obligation to meet all regional habitat goals, and we're presented with the appearance of trade-offs. You know, more of one means less of the other. This isn't true for estuarine beaches. Estuarine beaches actually do intergrade with and also interconvert with other estuarine habitat types. And in fact, the natural marsh berms that form at the edge of marshes are in fact a form of beaches. These have been documented since a century ago with some of the earliest studies of shorelines and shoreline processes. Beach deposits at the edge of marshes are trapped and formed elevated topography and drainage, which is colonized by salt marsh species. So those natural salt marsh berms are in fact beaches, and when they are reactivated by erosion, they turn back to beaches. Or if they are abandoned and removed from wave action, they rapidly colonize with vegetation and become these highly valuable salt marsh features. We do a lot to try to provide salt marsh islands or high tide refuges artificially, but they will form themselves if coarse sediment is introduced to the edge of salt marshes. You visit some of these salt marsh systems with beach edges at extreme high tide, perigee high tides, king tides, you'll see them sticking out. They look like linear vegetated barrier islands. One of the key contrasts between open coast beaches and living shoreline beaches that is very important for starting the early stages of the design process is to understand how waves interact with sands across the whole shore face profile. Sorry, I'm looking at the chat. It stops my thoughts. Um, oh, I'll show you a slide of some ocean beaches, but one of the key differences between ocean beaches, open coast maritime beaches, and estuarine beaches is that almost all the beach volume, sediment storage, and shore transport is in the beach itself. It's in the beach face, the swash slope, and the backshore, and that's it. There is very limited cross-shore transport of sand or gravel in the low tide terrace below it. So there is some connection, but at low tide and even mid tide and lower, waves are pretty much cut out and not doing very much at all to the beach. So they're really only operative at the highest tide stages. That's when sediment transport can occur. We don't have bar migration across low tide terraces. That's the rule. There are a few exceptions to the rule, very localized, which is why you have to be very site specific. San Lorenzo Creek Delta has some migrating bars. Point Pinole Creek has migrating bars. But generally speaking, estuarine beaches lack that near shore bar and migrating intertidal bar dynamics. So these low tide terraces are often flat, dissipative profiles that sap the wind wave energy or the refracted swell from the Golden Gate if you're close to the Golden Gate. And they do sometimes include small amounts of sand, usually finer than the beach face itself, which has a different role in the renourishment of beaches and their recovery from storm erosion. So really different dynamics. Next slide. Okay, so here, just to reset your eyes, here are some examples of both directly exposed Pacific swell beaches, Ocean Beach in San Francisco at the right, and a more sheltered, refracted swell approach of Duran Beach and Bodega Bay, very similar to Stinson Beach. Here, there are one or more series of bars in the shore face profile. Some of them are intertidal, some of them are actually in the shallow subtidal zone. They trip and break waves, so the waves start to lose their energy far from the beach face itself, and there's sand transport right across the profile at high magnitudes. In fact, there's usually more sand stored in the near shore and the low tide terrace than there is in the beach berm itself. That is the polar opposite of estuarine beaches, where almost all the beach material is in the upper beach profile. We also have processes like rip currents, which can push sand seaward beyond the breaker zone. Does not apply to sand transport dynamics of estuarine beaches. So back to one of our estuarine beaches, you can see there is confinement pretty much in all cases of beach-sized material in the beach slope, the beach face itself, and the berm. And the next slide will show and again, there's no intertidal bars, no bar dynamics, no surf zone to transport sand. Next slide. And here's the exception to the rule. These are good indicators. You can, from the field, you can feed into models. Here's the summer condition of Marina Bay Beach, which is another reference beach I'll be showing you again. In the summer condition, you can see that waves, both wind waves and long period swell, can winnow out a little bit of the fine sand in those low tide flats, and they can form oscillatory ripples. These are the ripples formed under unbroken waves. And there's a little bit of shoreward transport, usually in grain sizes that are smaller than most of the sand in the beach. So there is some cross-shore transport, but it's limited, and it doesn't necessarily match a lot of the equilibrium grain sizes that belong in the beach profile. So again, very different from ocean beaches. Next slide. A little lag here, at least at my end.
There it goes. Yeah, and Peter, maybe like 5 more minutes.
Oh boy, okay.
Okay.
Maybe I'll skip a few slides that are going to repeat.
Okay.
This will show you again, there is a coarsening of the grain size distribution across the profile. This is Marina Bay Beach in Richmond. This is a self-constructed beach. And what we usually see at the top of the profile, we kind of expect dunes, and sometimes we'll see people describe these vegetated ridges as dune ridges. They may have a little dune sand cap on them, but for the most part, they are storm deposits of coarse sediment. They're either washovers or they are storm beach ridges, and a little bit of fine sand can blow over them and cover them with sand. But for the most part, there's not a lot of dune-sized material to blow in most of our estuarine beaches. Exceptions occurred historically around the Oakland, West Berkeley shoreline. So here are some key lessons learned. I'll try to summarize here about early stages of planning for estuarine beaches. First, geography is fate. That is my shortest version of trying to emphasize that the coastal setting and the site selection within it really is both the source of meaningful goals that are feasible to apply, and it also is the source of appropriate design objectives and design options. So rather than develop abstract goals generalized from other projects, other sites, or other plans, start with an understanding of the vicinity of the sites you're focused on initially and build out from there. The second practical set of advice for beach planning is to move technical guidance to the front end of the process. Traditionally, I think it tends to come in during the permit application process, kind of in the mature stages. I think it's most useful to do this during the grant proposal process and the request for proposal stages. Those are the formative stages that kind of, I won't say constrain, but they do predestine a lot of the subsequent evolution. It's much more efficient to get that guidance in early on in the pre-request for proposal stage. Again, emphasizing the representative, relevant, local reference beaches to develop valid conceptual models based on field evidence. There is inherent uncertainty in the application of models. There's nothing wrong with models. They're useful tools, but there's always uncertainty in models. And one way of bracketing them, short of calibrating them with even more studies, is to use empirical references to set bounds to what is predicted versus what actually shows up in the range of variability of the coast that you're concerned about. And again, there's a caution because most engineering models and geomorphic models for beaches are developed for open ocean coasts. I think we're in the early stages of getting estuarine beach models, and I'm not holding my breath. they're peculiar systems. So again, what we have to work with are reference sites, and so far they have been very useful guides. Second, you have to be parsimonious in data collection. You can't use a dragnet approach for getting every possible source of data out there to support a project. So apply critical reasoning. What do you need to know and why? How will you apply it to evaluation of the project, monitoring, and design? Be selective about what you need to know and see if you can use proxy data sources to avoid collecting more data than you can actually use and avoid the risk of obscuring the data that are really going to inform your project by having too many things to look at. And the last recommendation that is very practical, this is getting down to what Roger will be talking about, is the importance of securing beach material sources that are suitable for the site and thinking about construction, equipment, and methods early on in planning. This is very much like the site and setting guidance that kind of predestines what is going to be feasible. I probably don't have a whole lot more time left. Shall I advance another slide? Okay.
Yeah, how about one more, Peter? Yeah, all right.
Okay, I'll just cut off at Bay reference beaches. We do have I can probably just run through two more slides as I speak. We have a range of reference beaches out there. Many of them are semi-natural. There are various combinations of natural materials, artificial materials eroded from artificial sources, or natural processes working on relocated natural sediments. There's all kinds of combinations out there. Unlike tidal marsh restoration, where we tend to look for the most pristine examples available to guide us, with estuarine beaches, if you want to go on one more slide or two more slides, I can show you we do have some pristine historic beaches that are, this is again, a semi-natural beach system, radio beach. These are natural processes. Just one more to show you the pristine beaches. you don't necessarily have to refer only to the best, most pristine beaches to guide living shorelines. They are out there, and there's more than just in these slides. And they're a really good starting point for starting beach design. We'll probably just cut it off there. There's always more information. Um,
Thanks so much, Peter. Yeah, that was fantastic. And we'll share the full complement of all of Peter's slides um, as part of the share out from this collaborative meeting. So there's some great questions that you've gotten in the chat. And um, I guess, I don't know, Jeremy, if there's any particular one we want to bring out from the chat for Peter.
I think we covered. I think we've Marilyn and myself have answered some of the questions there. It's a great interest, particularly on the open coast as well as in the bay. And of course, we're very focused on the open coast, on the bay itself here. There's one question about the role of the management of the consideration of wave energy in the design of the beaches, and um, how does that incorporate? How do you incorporate the exposure of the beach to waves into the design, um, Peter?
Well, again, if you're starting with a place where there is a remnant beach, you can start by looking at the behavior of whatever beach or partial beach profiles are there. If you don't have a beach where you're thinking of putting one, then the next step, I think, would be to look at the closest approximations of a reference beach you could use with a similar kind of wave exposure. There are lots of different ways of either modeling or measuring waves. Another way of cheating, which we did at Arambaru Island, is we place little pockets of different size sediments out ahead of storms, which are usually the limiting factor of where sediment is transported. Put little spray painted strips of different size materials, let the storm go by, and watched where they drifted. It's sort of a cheap, fast, not particularly analytic, but a good initial preliminary data source about what is moving and how fast in a place where there is no beach to measure to get a long history of, say, background data on profile adjustment. You can see how mobile different grain sizes are. So those are at least three different initial approaches: reference beaches, modeling, and the sort of shortcut method of laying out different sample sizes. These are all de minimis, so it's not regulated fill placement. These are like bucket size, sandcastle size amounts of beach sediments you can play with.
Peter, I'm going to reshare my screen and one slide that we didn't get to where you mentioned the different beach materials. This would be a great one to cover if you want to speak to it before we move
Sure,
on.
this would be a talk in itself, and that was how I was going to lead into the slide. But I could start at any end. Most beaches, as you know, are sand beaches in San Francisco Estuary. There are differences between sand beaches. There are different sources and grain sizes. Most of the ones we use in living shorelines are medium and coarse sand because they have slightly steeper slopes, narrower profiles, a little more resilient. Fine sand beaches are very dissipative. They need wide areas. They're great for restoration, but they're not a first reach for living shoreline projects in most cases. They can be included. The key one that again is a hard sell because it's hard to predict them, is shell hash. I just would point out that the earliest maps of San Francisco Bay, the largest fonts or lettering sizes in those old maps were about the distribution of shell banks and shell muds. They even wrote dead oyster shells in the 1827 maps. This really distinguished San Francisco Bay from the rest of the ports and estuaries in the West Coast. There's a lot of this material here, and actually a lot of San Francisco Bay beaches have a major shell component. The difference is that the shell mounds were probably from that era. These are fossil shells. They're not related to late Holocene, wet, cool, freshwater pulse era. These are from earlier sea level stands, massive concentrations. The point is they build different kinds of beaches that are not well studied. They have some aspects of gravel in that they stack really steep. They are flat pieces, they're flakes and fragments that imbricate, they lock into each other, so they can make vertical slopes, but they're also super light and they float off at low settling velocities. And they drift a lot. They're more like I've got some over spill. Someone's got go on mute. Anyway, they are the underexplored beach material. There's a lot of it. Again, one thing I didn't get to talk about a whole lot was the beach compartments, whether they're swash-aligned, confined pocket cove beaches with limited longshore transport. Shell hash beaches work very well in areas of confined transport, but they are very prone to drift if you're not in a confined compartment. Gravel you can place almost anywhere because it adapts to the widest range of wave energies. And I'll cut it off there.